I'm Christian Bettstetter. I'm professor for mobile systems at the University of Klagenfurt, where I'm leading the Institute of Networked and Embedded Systems. My research topics include wireless communication and self-organizing systems. And one of these self-organizing systems are Swarmalator systems.
My name is Udo Schilcher and I'm a senior scientist in the Mobile Systems Group at an Institute of Networked and Embedded Systems.
So my name is Kevin O'Keefe. I'm from Ireland originally, but I went to America from my graduate work, and that's where I started working on the Swarmalators. So I was working kind of in complex systems broadly. I was interested in synchronization. My advisor was Stephen Strogatz. He's sort of big in that space, so it was natural I would work there.
Each robot contains a motor that provides the locomotion capability so that the robot can move around. Secondly, it contains a communication module. In this particular case, we use a Bluetooth module. Further on, it has a display. On the display, we present a marker to identify the robots. This marker is then basically filmed by a camera that is on top of the system and can see these markers and identify the robots and also find their location. And finally, the robots contain colored LEDs that represent the internal phase in a color-coded fashion. The robots use their communication capabilities to share all the locations and internal phases among each other. And these phases are used to calculate the movement vectors and internal phases. So the robots, once they know where the other robots are, they can basically move towards other robots that have a similar phase and away from robots that have a very different phase, or the other way around. And with that capability, they can form these different patterns depending on the parameters selected for the model.
So Swarmalator systems are controlled by two parameters, J and K. The parameter K is responsible for the synchronization of the system. If K is 0, nodes do not change their phase. If K is positive, they will synchronize. If K is negative, they will desynchronize. The parameter J determines the coupling between synchronization, so temporal coordination, and spatial coordination. It basically tells us whether nodes that are already synchronized also spatially attract or repel each other. So the two parameters J and K determine which of the 5 basic patterns we achieve. For example, if K equals 0, all nodes will arrange along a ring, an annulus, in an ordered way. Ordered means that they sort according to their phase. If we have a low value of J, we either have all nodes synchronize on the disk or desynchronize on the disk. And for other parameters, we get an active phase wave or a splintered phase wave. These are the 5 basic patterns.
That was my advisor, Stephen Strogatz. I wanted to call them swarming oscillators. And then he just looked at me and said, Swarmalators. I was like, yeah, that's easier. Just squash them together. The hard part is making the model general enough that it produces something that's realistic. You know, the states actually map on to real world systems, or at least look like them somehow, and also making it solvable. So that was the hard part, coming up with a model you could actually solve some things. So that took about a year.
The internal phase, in principle, is a value that is in the range from 0 to 2 pi. The phase is connected to the movement in a way that similar phases attract or repel other robots depending on the setting. This could lead to patterns that cannot occur if there is no internal phase. Let me give you an example. We look at the active phase wave state, as it is called. There, the robots move in a certain way because of the phase. This movement brings maybe 2 robots together that have phases that are very different. Then the phase is updated, so they become more similar and more similar. And again, this triggers some movement, and this is a circle that goes on. and so the movement never stops. That's why it's called an active state. But of course, the face could also represent other properties from a real-world application where this algorithm is used. For example, you could think of the face as a battery state of the device, so that maybe devices that have similar battery states are coming close together and doing a task that consumes more energy than others where the battery is almost empty.
In the Swarmalator system, each Swarmalator communicates to all other Swarmalators because they have to exchange their states. So each Swarmalator has to know the position and phase of all other states. Otherwise, it doesn't work. We invented a model where we are closer to reality, where each Swarmalator just communicates with its direct neighbors. But then all the neighbors forward the state information to their respective neighbors. And in this way, again, we achieve global coupling and the system emerges to one of the 5 basic patterns.
In the biomedical sphere, they have like micrometers or chemical robots, whatever you want to call them. You have collections of particles and you can steer them with magnetic fields, and they can do all sorts of cool things in biology. One example is like tumor killing. So you imagine you got a blood vessel, it's like a thin cylindrical pipe, and there's some blockage coming up there and you want to remove the blockage. They can send in like these colloids of Janus rods, just a little stick, and you get them to twirl. So they go in as kind of a swarm, and then you want them all to twirl at the same time. And once they're twirling, they kind of go through the tumor and break it down.